Let's look at the standard matrix for a linear transformation. Let T from Rn to Rm be a linear transformation. Then there exists a unique matrix A such that T of x equals Ax for all x in Rn. In fact, A is the m by n matrix. Holy cow, this is getting complicated, but you'll be fine. A is the m by n matrix T of E1, T of E2, blah, 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 blah. And remember what those represent? Those are the columns of the identity matrix. So in other words, A is the m by n matrix whose jth column is the vector T of E sub j, where E sub j is the jth column in the identity matrix I sub n. There's no way you're going to understand that based on what I just said, but you'll be fine. We'll look at some examples. The matrix A that we just talked about, this is the standard matrix for linear transformation. In other words, it's the matrix A such that T of x equals Ax. The above theorem tells us that we can determine the entries in the standard matrix for T by looking at what T does to the columns of the identity matrix. So here's an example. Find the standard matrix A for the linear transformation T of x equals 3x. So T of x equals 3x. In other words, this transformation would multiply a vector by 5, or multiply a vector by 3. So 3 times, let's say, I don't know, 1, 2, would give you 3, 6. Okay, that's the transformation we're talking about. So the standard matrix for that linear transformation, all we have to do is look at what T does to the columns of the identity matrix. And in this case, since we're talking about 2 by 2, the inputs and the output are 2 by 2. We'd have 1, 0, 0, 1. So what does T do to 1, 0? Well, it would multiply it by 3, so you'd get 3, 0. What does T do to 0, 1? Multiplies it by 3, gives you 0, 3. So this is the matrix that corresponds to this linear transformation. And if you want to test it, just try it. Ax, in other words, 3, 0, 0, 3, times 1, 2, notice that gives you 3, 6. So indeed, this is the matrix that corresponds to this linear transformation. Let's look at the standard matrices for various linear transformations. Let's take reflection across the x-axis. Okay, so if you reflect a point across the x-axis, what does T do to 1, 0? Okay, so here's 1, 0. When you reflect 1, 0 across the x-axis, you just get 1, 0. So T of 1, 0 is 1, 0. Now T of 0, 1, when you reflect that across the x-axis, you get 0, negative 1. So the matrix that corresponds to the reflection across the x-axis is 1, 0. It's basically 1, 0, 0, negative 1. Use this to reflect the point 3, 4 across the x-axis. So again, one way you could reflect the point 3, 4 across the x-axis is to multiply by the matrix we just found. That is the standard matrix for this linear transformation. When you multiply this, you end up with 3, negative 4. Let's see if that's the case. Where was 3, 4? Here was 3, 4. And when you reflect it across the x-axis, you do indeed end up with 3, negative 4. So it worked. Now, obviously, we wouldn't go through all of this to reflect the point across the x-axis. It's a lot easier to say that 3, 4 goes to, 3, negative 4. But there are some circumstances when it's helpful to have it in matrix form. Again, let's look at the standard matrices for various linear transformations. How about reflection across the y-axis? T of 1, 0. Okay, reflect across the y, that's going to be negative 1, 0. T of 0, 1, that just stays 0, 1 when you reflect it across the x-axis. So we end up with negative 1, 0, and 0, 1. That's our matrix. Reflection across the line y equals x. 1, 0 ends up at 0, 1, and 0, 1 ends up at 1, 0. So that's our matrix, 0, 1, 1, 0. Reflection across the line y equals negative x. Again, this is going to work out to be 0, negative 1, negative 1, 0. Horizontal contraction or dilation by a factor of k. So in other words, so you've got a point here, and if you contract it horizontally, that means it'd be going this way. If you dilate it horizontally, it'd be going this way. So if you did that to a bunch of points, for example, this smiley face would then, be stretched out. It would look something like this. Still be a smiley face. Okay, so T of 1, 0, you've stretched that by a factor of k. So now it's going to be k0, although you might contract it. It's still k0. And t of 0, 1, well, it's a horizontal contraction or dilation, so that still stays 0, 1. So this would be our matrix, K0, 0, 1. In the same way, a vertical contraction or dilation by a factor of K would be 1, 0, 0, K. And if it's vertical contraction, that means something that looked like this now looks something like this, if you stretch it. Rotation about the origin through an angle of pi radians counterclockwise. Okay, if you start off at this point, 1, 0, and you rotate it pi radians, you'll end up with negative 1, 0. And in the same way, if you start off with this point, 0, 1, you'll end up with this point, 0, negative 1. So that's why we get this. That's the matrix for this linear transformation. Horizontal shear. Here's what horizontal shear looks like. You start off with a square that looks like that, and you end up shifting it diagonally. So you'd end up with something like this. Or, if it's a really intense shear, if it's something more intense, that you'd end up with something like this. Okay, it's depending on how much you shift it. So t of 1, 0 ends up being 1, 0. But t of 0, 1, that ends up being k1. So what used to be here is now here. So again, it's just a matter of how far this is. If it's a factor of k, if you shift everything over, not by a factor of k, but really shift everything over by k units, then it's a horizontal shear that corresponds to this. Okay, so that would be your horizontal shear standard matrix. Vertical shear in the same way. For a vertical shear, you start off with a square that looks like this. A vertical shear would end up giving you a square that looks like this. Okay, and again, that's where this distance k is your factor. Projection onto the x-axis. Here's what that looks like. If you start off with the point 1, 0, that just stays 1, 0. But when you project things onto the x-axis, that means everything gets squished onto the x-axis. So what used to be here, for example, 0, 1, that's now at the origin. So that's at 0, 0. So it looks like 1, 0, 0, 0 is the standard matrix for that linear transformation. In the same way, projection onto the y-axis, so any point here, like at 1, 0, that ends up at the y-axis, 0, 0, and this point 0, 0, 1, that just stays at 0, 1. So this is what our linear transformation looks like. Okay, now a mapping T going from Rn to Rm is onto if each b is the image of some vector in Rn, and a mapping T is 1 to 1 if T of x implies x equals y. That is, no two vectors map onto the same vector. That's what we mean by 1 to 1 and onto. Let T be a linear transformation with this standard matrix. Find n and m. Oh my goodness. Okay, well, let's ask ourselves, what vector would we need to multiply this matrix by in order to get something? This is 4-dimensional, so this matrix would have to be 4-dimensional as well. So it looks like you plug in a 4-dimensional vector, and when you get that, you end up with a 3-dimensional vector. Because this is 3 by 4, and this is 4 by 1, so the result is going to be 3 by 1. So it looks like n equals 3, n equals 4, and so this is 4, and this is going to be 3. So n equals 4, m equals 3. Is the mapping 1 to 1? No, because the equation ax equals b has a free variable. There's one last cool transformation that I'd like to show you, and that is if you rotate something, an angle of phi radians counterclockwise. Okay, so the linear transformation that corresponds to that is going to be, it's going to be cosine phi, sine phi, and then negative sine phi, cosine phi. Okay, that's one last cool one. Thought I'd show you that.